This is our formal lab on finding the charges of balloons. The main problem that this lab works to address is how we can find the charges of two objects. Our main punchline is that we weighed each balloon separately and charged them up using a specific method. We then placed one balloon on a scale and observed how the weight value changed as the second balloon approached it. Our motivation for conducting this experiment is that finding the charge of a specific object can implicate its use in further scientific areas, such as engineering and medicine. Our experimental findings were the specific charges of the balloons, and that the balloons in trial 1 and 2 attracted, and the balloons in trial 3 repelled. Here is an outline of our experimental procedure. We blew up two balloons of relatively equal masses, balloon 1 being 2.65 grams and balloon 2 being 2.56 grams. We rubbed both balloons on a sweater for about 10 seconds. Balloon 1 was placed on a scale while balloon 2 was held at a constant distance above the scale, which was 80 centimeters. We moved balloon 2 towards balloon 1 by hand at approximately 3 centimeters per second. We recorded the change in weight of balloon 1 as balloon 2 approached but did not touch balloon 1. The trials ceased just before the balloons made contact with one another, and 3 trials were conducted. Here's our experimental limitations. First, the balloons may not have been charged for the same amount of time within and between trials. This could cause a difference in the calculated charges of the balloons across trials. Additionally, the balloons were left to idle for different periods of time across trials due to inconsistency with starting each trial. This could cause the charges to deteriorate over time and produce inconsistent calculated charges. Also, if balloon 2 didn't start at the same height across all trials, that could cause premature weight changes early in the trial, affecting the calculated weight change and therefore the charges. Finally, the angle of the camera made it hard to measure the distance between the balloons accurately. Some ways we tried to minimize error are we charged up the balloons for an equal amount of time for each trial, we kept balloon 1 and balloon 2's roll the same for consistency, and we conducted 3 trials.
So here we have experimental expectations. So here we're focusing on the electrical force with equal to Kc, which is Coulomb's constant, times Q1 and Q2, the charge of both balloons, and R being the distance between them, and R high being 1 in this case due to the vertical and linear motion. So Q2 is equal to balloon 2. Balloon 2 is at a fixed position, and balloon 1 is being brought closer. So now here we have representations using pie charts and free body diagrams. So for repulsion, we have the potential energy increasing, becoming more positive, and the kinetic decreasing as balloon 1 gets closer to balloon 2. Now for attraction, since this attraction, the balloons are getting closer to each other, potential becomes more negative, and the kinetic also increases as well. So now for free body diagrams, since balloon 2 is at a fixed position, we know that Fg is present, and the weight that changes on the weight scale is the change in force, and that change in force is equal to the electrical force that balloon 1 is putting on balloon 2, and then just also equal and opposite to the electrical force that balloon 1 gets from balloon 2. So for our data, we looked at our videos and measured the change in mass for each position, starting from 3 centimeters all the way to 1 centimeter. And we use this to later find the average when calculating Q for both balloons. And now we assume that both of them are equal. So now we do that for all 3 trials, and we have our data. And then we graphed it using the change in force, using F is equal to ma, Newton's second law, to find that change in force from the Fg that is equal to the electrical force that is present at 3 centimeters, 2 centimeters, and 1 centimeter. And we do that for all 3 trials.
So for the results that we got for trial 1, the way we analyzed it was for each distance, which was 1 centimeter, 2 centimeters, and 3 centimeters, we took the change in weight, and then we multiplied that by the acceleration of the Earth or gravity, and to calculate force. And then once we got force, we plugged that back into the equation for electrical force, for each distance. So, for example, for t equals 1, we had a force of negative 0.98, and we set that equal to Coulomb's constant multiplied by q squared divided by the distance squared. And the reason we use q squared for this equation was because since we charged both balloons the same way, we assume that they have the same charge, and so we just condensed them into q squared. And then we calculated the q value for each of these equations, and once we got those q values, we took the average of all those charges that we got and divided by 3 to get the average charge of each balloon. As you can see here for trial 1, we got negative 1.52 times 10 to the negative 7 coulombs. Sorry. And we did the same process for trials 2 and 3. So for trial 2, we ended up getting a result of negative 1.13 times 10 to the negative 7 coulombs. And then for trial 3, we got a value of 2.31 times 10 to the negative 7 coulombs. So in conclusion, in trials 1 and 2, since the weight on the scale was negative, and the approaching balloon was, that means the approaching balloon was opposite in charge to the balloon that was on the scale, because as the top balloon was approaching the balloon on the scale, it pulled on the balloon on the scale, thus making its weight negative. And we can also see that since in the calculated charges, they had negative values. And then for trial 3, since the weight on the scale increased, the approaching balloon was the same charge as the balloon on the scale. And this is because as you bring the incoming balloon closer to the balloon on the scale, they push on each other, so the weight increases. And you can see that because the charge of balloon in trial 3, the charge of the balloons in trial 3 was 2.31 times 10 to the negative 7. So overall, to answer the original problem, in trial 1, the calculated charge was negative 1.52 times 10 to the negative 7, and the balloons attracted. The charge of the balloons in trial 2 were negative 1.13 times 10 to the negative 7, and the balloons also attracted. And then finally, for the charge of the balloons in trial 3, we calculated 2.31 times 10 to the negative 7, and the balloons repulsed.